So I am Fethiye Irmak Dogan, and I'm a postdoctoral researcher at Effective Intelligence and Robotics Lab. And this is our last Christmas celebration photo with some of the group members. And today we'll talk about explainability for human-robot interaction. What is explainability for robots? Explainability is a mechanism to understand why robots make the decisions they make. So basically interpreting and understanding the reasons of such decisions. And since they should convey these reasons, they should be easy to understandable form to humans, as well as it should be in a concise form, and it should include all the relevant information about the decision-making process. Why do we care? Why do we care about explainability for robots? Our research group is interested in deploying social robots into human environments to help them to facilitate their lives. And this brings a lot of challenges, such as understanding users, their verbal, non-verbal cues, as well as the interaction environment, the social appropriateness of actions. So there are such challenges. And in these challenges, to ensure robots' ethical and transparent integration into human lives, explainability plays a critical role. That's why we are interested in explainability. And there are varying applications of explainability for human-robot interaction and social robots. And specifically, I'm going to talk about two use cases in this presentation, how to use explainability. The first one will be about generating robot explanations for an object search in an ambiguous scenario when you give instructions to a robot, but there are ambiguities. And the second one will be about using human explanations. The other way around. This time, the robot will use human explanations in order to generate socially appropriate robot actions. Let's start with the first use case, how to resolve ambiguous situations leveraging robot explanations. So, ambiguities in natural language instructions are inevitable, right? In even such a simple instruction, can you hand me the green vegetable? There can be ambiguities. There can be multiple objects fitting to the object description, and such ambiguities can frustrate all of us. And what are the previous limitations? If you ever interacted with Siri or Amazon Alexa and gave an instruction, and whenever it doesn't understand you for some ambiguities or uncertainties, it would only tell you, oh, sorry, I couldn't catch what you said, or I couldn't get the instruction, rather than really understanding what was the reason that you couldn't understand. So this is one of the previous limitations. Another one is previous work assumed that target objects are given or can be obtained existing object detection or localization methods. Meaning that in this example, this is Brussels sprouts and this is kale, and existing systems cannot easily detect such objects in a scene. So whenever they are not detected, they are not considered as the target object candidates. Those systems will fail to detect this as the target ones. Last but not least, they didn't ground from the understood parts of the user request. So maybe the robot is not familiar with the vegetable context in this example, but maybe it knows some green objects in the environment, what a green object is. So it can now focus only the green objects in the scene in order to find what the user is asking. So to address these three limitations, we suggested an interactive system that used follow-up clarifications, such as this one. Is it on the cutting board? And if the user says yes, then now we know which object the user is talking about. So we suggested this clarification system by using robot's own explanations, and robots use the known objects in the environment, as well as the understood concepts from the user's request. Let's move on to our methodology. How did we manage this? Again, a very similar example. Can you hand me the green vegetable? First, the robot found the candidate objects, meaning the regions that are causing the ambiguities in the instructions, by using the GraphChem explainability module. GraphChem explainability module highlights the scene regions that are contributing to the prediction process. So here, it shows actually what are the regions that are causing the ambiguity. Here, the first bounding box shows the first candidate region that can be the reason of ambiguity. The second one is the second bounding box, so on and so forth. After finding these candidate scene regions, the robot detected objects in the scene by using a transformers-based network. Here, knife, banana, spoon are detectable objects, but there are undetectable objects as well, like artichoke, bell pepper, the basil. These are non-detectable objects. So it detected the ones that are detectable by existing object detectors, and we have the candidate objects. And by using the spatial relations between the candidate objects and the detected objects, the robot generated follow-up clarifications. For instance, for the first candidate one, it asked, is the green vegetable to the left of the banana? And if the user says yes, it is, then we know which region to look for in order to identify the described object. This was the very brief summary of our methodology. And to understand if really our methodology works in the real world, we conducted a user study. In this user study, people described objects to a robot in this ambiguous setup, and the robot tried to find the described object. Let's watch a quick video. Before going to that, sorry. We had two conditions in our study. In the control condition, whenever there were ambiguities, the robot would ask users, can you describe the object again? As if in Amazon Alexa would do. But in the clarification condition, it would ask the follow-up clarifications by using our method. Let's see the video.
The bottle next to the knife.
Can you describe the object again?
The bottle next to the knife. The spoon on the right side of the table.
Is the spoon to the right of the bottle from your viewpoint?
Yes.
Check the red box on my tablet to see whether it is the object you're describing.
Yes, it is.
So this was from one participant from our study. And the main takeaway of this study was whenever there are ambiguities in the interaction, follow-up clarifications were helpful for a robot to understand the described objects. So we talked about how we can use robot's own explanation to identify ambiguities and resolve them in a follow-up clarifications in the first use case. And then now in the second use case, we are going to see how human explanations can be used to generate socially appropriate robot actions. So we expect robots to operate in human environments and perform very complex tasks, right? Carrying heavy objects, I don't know, doing the cooking, vacuum cleaning, doing the dishes for us, all these complex tasks. But we still expect them to follow our social norms and preferences while doing these complex tasks. For instance, in a scene like this, whenever there are kids around, one user might prioritize safety and expect robot to not to carry large objects when the kids are around. But another user might prioritize efficiency and say that the robot should be quick at carrying such objects when the kids are around. So there are such human preferences that should be integrated in the robot's decision process. To address this, we propose the GRACE system, which integrates common sense reasoning together with human explanations. In GRACE system, we use manners dataset, and this scene is actually taken from the manners dataset. And this includes some synthetic scenes and the social appropriateness of robot actions, such as vacuum cleaning, starting a conversation. Basically, humans annotated each of these scenes based on the social appropriateness of the actions. And as well as the social appropriateness, it also has the reasons for giving such social appropriateness scores. So here it can be the safety reasons, as we gave in this example, or it can be the human state, number of people in the scene, how close people are to the robot. So they give the reasons why they gave these social appropriateness scores. And by using this data set, we propose the GRACE methodology, which first has the image certainty classifier. This classifies for certain scenes where, for instance, there are not that many people, so probably people would agree among each other on their social appropriateness scores. We use LLM. We obtain the common sense reasoning through large language models, and we directly output LLM predictions. But for the more complex situations, when there are so many people and it's crowded scene, for uncertain cases that people might disagree among each other, we use a conditional autoencoder model. This conditional autoencoder model takes the LLM predicted social appropriateness scores, as well as the human explanations, so saying that you should prioritize safety, efficiency, whatsoever here, and it corrected the scores it tailored the scores based on given human explanations. So this LLM scores was tailored based on given human explanations with this autoencoder model. Thanks to its generative approach, this autoencoder model also could generate explanations for human given scores. So if the user gave such scores, probably they were prioritizing these or that. So this model could give such explanations for the given user scores as well. Now I'm gonna give you some grace-generated robot explanations for given user scores. Here in CNA, this line shows the user scores given for the social appropriateness, 5 being the most appropriate and 1 being the least appropriate, so very inappropriate per se. So these are the scores given by people, and these are the robot-generated explanations for given such score, why people would have give such scores. So in CNA, for instance, when there is only 1 person, the robot could correctly predict that its own actions were safe. In another scene, when it was very crowded, the robot could predict that it was too close to people in the scene. And in scene C, when there was someone lying on the sofa, you see here, the robot could predict, thanks to Grace method, it could generate that people are not available in the environment. So based on these given scores, probably people are not available for my actions. It could predict. To conclude my presentation, I talked about 2 applications of explainability for human-robot interaction. The first one was in an object search scenario to resolve ambiguities. And the second one was how to use human explanations in order to generate socially appropriate robot actions. And I would like to conclude my presentation by saying that explainability is critical in order to ensure the trustworthy and interpretable integration of robots into human lives. Thank you so much for your kind attention, and I am happy to answer all your questions.